The next thing we want to discuss is called the nuclei. We probably need to actually look at these two things at the same time. So nuclei and the radionuclei. The difference between the two is the radionuclei is actually the species that's not stable. It's going to undergo a radio decay. Not every atoms are stable. So that's why we have these things called the nuclei and the radionuclei. There are around 271 stable nuclei in nature. We will just talk about how many atoms we have on our periodic table. 114, right? And here I tell you actually there are actually 271 nuclei. Because this is actually a number including the isotopes. There are 271 stable nuclei. There are also many others is not stable. So those non-stable nuclei is going to undergo radioactive decay. If you have number of protons larger than 83, it will be radionuclei. Okay, that means actually it is not stable. And it's actually very easy to actually see why it is not stable. An atom is actually a very, very small particle, right? So how small is an atom? The size of a protein is 5 to 10 nanometers, 10 to the negative 9 meters. So one single protein probably composes more than 10,000 atoms. Okay, that means actually the average volume of one atom will fall within like femtometers or even smaller. Okay, so it's actually extremely small particle. And inside a particle, you are going to throw in 83 protons. So proton is actually a positively charged species. So we know when you put the positively charged species together, they repulse each other, right? Okay, now think about, okay, you have an atom so small, you have 83 protons inside. In principle, it should not exist. But, okay, we do see the atoms contains many, many protons. So in the high energy physics field, they create a term called the strong force. So they think these things can happen simply because in our atoms, there's actually a very special partner called neutrons. So they think the neutron is actually the species that actually make all the things possible. Of course, we're not going to talk about the details. In this chapter, we're going to focus more about if you have a non-stable nuclei or radioactive nuclei, it's undergo decays. We want to actually learn about those decays. To make sense all of these decays, I want to actually introduce you one thing called the nuclear equation. These things will always be true. So assuming today you have atomic symbol X, Z, and A, it's undergo radio decay. Then you produce S, B, and U plus T, C, and V. Assuming your atoms undergo a decay, produce some other species, let's call S and T. Then one thing that needs to be always true is that A has to be the sum of B and C. Z has to be the sum of U and V. Okay, so this has to be true all the time when you write out these equations. Okay, so that's actually step number one. Okay, with these things in mind, then we can start to talk about the type of decays you are going to see if your nuclei is actually not stable. The first type we are going to say is actually the alpha production. So that's type number one. When atoms undergo alpha decay or alpha production, you will always see helium-24 appear. So helium-24, less specific species, is so-called the alpha particle. This is something that you need to actually memorize. When every time you see, okay, one atom undergo alpha decay, that means in the product side, you're going to actually produce helium-24 species. Type number two, if today inside a description you see some atoms actually undergo a beta production, that means it's going to produce electrons on the product side. So this thing is so-called the beta particle. So the electrons is actually so-called the beta particle. It actually carries -1 charge. And then the third type is actually so-called the gamma ray production. So every time you see this gamma ray production, you are going to produce the gamma radicals, which is this guy. You see a symbol of gamma, but that gamma doesn't actually contain any protons, and it doesn't contain any mass. A very weird particle here, but it's an alpha particle. And then the very last one is so-called the positron production. Positron is short for positive electron. So positron is actually positive electrons. So its symbol will be, okay, you have this E, which is the same as the electron, but the charge, instead of -1, it becomes +1. The mass number is actually 0. So these are the 4 different decay particles that you are going to see in this chapter. What you're going to get tested is that if today I say I have uranium-238 undergo a alpha decay, what will be the product? So that will be the question you're going to encounter. If today I have uranium-238 undergo a alpha production, from that description, you should be able to write this. That is actually your starting materials, right? And then you actually undergo alpha decay. Therefore, you know on the product side, you're going to have helium-4. And then I'm actually asking you, what are the things that remains? This will actually the answer you want to provide. And the way you figure out the answer is simply because you know the nuclear equations. So you know, let's focus on your atomic number or the proton number. So you know initially you have 92. Once you produce your alpha decay, then you know you already consume 2 protons. Therefore, you know the remaining protons has to be 90. So once you figure out, okay, the remaining proton is 90, then you go back to your periodic table. 90 is actually going to tell you, okay, you're going to have TH. So you know you can write TH90. And the mass number, originally you have 238. You know proton is going to use up 4. Therefore, you know your mass number will simply equals to 238 minus 4, that's 234. Therefore, you can figure out this answer. How to actually judge whether an atom is stable or not? So in your textbook, they actually provide a very simple rules. If you see an atom that have even number of proton and neutron, then it will be actually stable. Another rule is that some of the atoms will be super stable if they have the magic number of proton. And those number is 2, 28, 82, 20, 50, and 126. The way I memorize it is actually, it's just, first row is actually a combination of 2 and 8, right? 2, 8, 28, 82. And then for the tens, you only have 20, 50. 126 is exception. So if you see an atom that contains these matching numbers of protons, they will be actually very stable. If today I give you an atomic symbol, you need to first judge is it stable or not. If it is not stable, it's undergo a radio decay, right? So in the question is actually going to ask what kind of radio decay you're going to see. Your textbook is going to tell you if you calculate the neutron to proton ratio, okay, which also highlight us the N to Z ratio. So the N is actually your neutron, Z is actually your proton. The neutron to proton ratio of atom. Your textbook say, okay, if your N to Z ratio is too high, then your neutrons are going to convert to proton through beta decay. If your N to Z ratio is too low, then your proton is going to convert to neutron via positron emission or electron capture or alpha decay if the number of protons is actually larger than 83. So how do you define too high or too low? This is actually the table, okay, you're going to use. So you can see these tables actually break into 4 different rows. The first column tells you, depending on the number of protons you have, I cut it into 4 different sections. 1 to 20, 20 to 40, 40 to 83 and larger than 83. Okay, you're going to have 4 different groups. For these 4 groups, you can know the atomic number from your periodic table, right? So every time you see an atomic symbol, you will know what the Z is already. Then you need to predict, okay, whether this is actually stable or not. So how do you actually know it's stable or not? The easiest way is actually that if the number of mass is outside your atomic mass plus minus 2, then it is not stable. So the mass number is actually something that you are going to get from the questions. They will always give you a atomic symbol. For example, X, let's say 100. So they are going to always provide these things to you. How do you predict this is actually not stable? Of course, if it's actually larger than 83, it's never stable. So if Z is larger than 83, you know it's never stable. But if it's actually below to 83, then the way you judge whether this thing is actually stable or not is actually you compare the mass number here to the mass on your periodic tables. If the difference is actually larger than 2, then you know it's not going to be stable. If it is not stable, you need to actually know the threshold. If the threshold, if it's larger than the threshold, then you're going to always get the beta decay. But if it's actually below the threshold, then for the first 3 you're going to get the positron emission or the electron capture. So the threshold for different rows is slightly different. So it varies from 1, 1.25, and 1.5. For the first 3 rows, if it's actually smaller than the threshold, all you get is positron emission or electron capture. But if your Z is larger than 83, the threshold becomes 1.6. So 1, 1.2, 1.5, 1.6. So for the first 3 rows, if it's actually lower than your threshold, all you get is actually positron emission or electron capture. But for the Z larger than 83, you're going to undergo alpha decay. But if it's actually larger than your threshold, all of them actually undergo a beta decay. So those are the tables you're going to use. Okay, eventually to actually memorize this. We're going to go through a few examples now. I would suggest you actually put this table right next to you so you can actually reference back and forth. Okay, so here it says Y100 is radioactive. Okay, so this sentence alone already tell you the Y100 it's not stable. Because if it's stable, you won't undergo a radioactive process. So here you need to actually translate this. What is this? Okay, that 100 actually tells you the mass number. So you need to actually translate this guy into this. Then the next thing you need to actually focus on is actually what is the atomic number, right? So you're going to use your periodic table to find out what is the atomic number of Y. So if you look at this carefully, okay, you'll realize the atomic number is actually 39. So once you do this, then you should see that the number of protons is going to equals to 39. Number of neutrons is going to equals to your mass number minus your proton number. That's going to give you a number of 61. The next thing you do is actually you calculate your N to Z ratio, right? So your N to Z ratio is going to equals to 61 over 39, and that's going to equals to 1.56. You can see from the atomic numbers, you know it belongs to the second row of our table. So on the second row of the table, you know the threshold is 1.25. So the number we got is actually 1.56, which is actually larger than the 1.25 threshold. Therefore, you know this is actually larger than this threshold. Therefore, what you're going to have is just beta decay. That's how you actually use that table to make the prediction. Okay, so let's do another one, S28. So the first thing you do is actually looking for the atomic number of sulfur, right? So what is the atomic number of sulfur? It's 16, right? So you know the number of protons is going to equals to 16. Number of neutrons is going to equals to 28 minus 16. That's going to give you a value of 12. Therefore, you can calculate your N to Z ratio. It's going to equals to 12 over 16. And that will give you a value of 0.75. So once you figure things out, then you go back to the table, right? So it's actually the number of proton is actually 16, right? That belongs to the first row. Therefore, your threshold is 1. So right now, what you get is actually 0.75, which is below than 1. So all you get is going to be positron emission or electron capture, okay? So let's actually how you do all this prediction. Right, every time you see this keyword radioactive, it means actually this is unstable, right? Then you can actually immediately apply to the tables we provide. But if today I just tell you this, okay, if I erase this, first I can ask you, okay, is U235 stable or not? If that is the question I ask you, okay, what you need to do is actually you check out the periodic table of the U235. The atomic mass of uranium is actually 238. Okay, and then compared to the mass number you have here is actually 235. The difference is actually larger than 2. Then it is unstable. And then once you know it is unstable, then it's undergo a radioactive decay. Then you will be able to answer, okay, what kind of decay you are going to see. U235, the atomic number is actually 92. Therefore, you know the number of proton is 92. Number of neutron is going to equals to 235 minus 92. That's going to give you a number of 143. So from here, then you can actually calculate your N to Z ratio, which is going to equals to 143 divided by 92, and that's going to give you a number of 1.55. Since the Z is actually larger than 83, right? So you will know that, okay, the threshold we provide here is 1.6. If it's actually smaller than 1.6, then you're going to have alpha decay. If it's actually larger, then you have beta decay. So since the number we have is actually 1.55, right? It's actually smaller than 1.6. Therefore, what you have is going to be alpha decay.